Hello, folks, and welcome to Answer Everywhere. Today, we are taking a look at the Flipper Zero firmware. For folks who are not familiar with Flipper Zero, it's like it's a little hacky device that is kind of like if you took an Arduino and put a bunch of functionality in it and then made it look like a Tamagotchi. And it looks like that. And it can do a bunch of hacky stuff, like it has RFID reading and, I guess, speaking, transmitting, and you can do things with it. I don't know, let's look for hacks. Flipper Zero hacks. Well, here's maybe a collection of things you can add to it or whatever. Bank vault of amiibos. IR dumps. You can control anything, I guess, that's controlled by infrared. You can presumably control televisions and also like speak to garage door openers and corporate thingamajiggies that speak these things. So that's the basic idea. This is the what we're looking at is the software, because I'm not sure, first of all, is there hardware? Hardware. No? Just out of curiosity. I don't know if the hardware is open source. I guess it's mainly a board, and then there would be some like 3D print style models for the casing. So here's the ST link, this thing, do some apps catalog, and then some debug stuff, and then some tools. And it has some apps. So I don't know what the apps look like, so let's just look up a screenshot. How about iOS? So it looks like this, I guess, lots of orange, and you can, I guess, speak to the device. So here's some application catalog. I guess we're going to ignore that. DevLink. This has been archived. Okay, so here's the development board based on ST-Link v3. I don't know what that is. A modular in-circuit something or other. Debugger and programmer. Okay, so I guess it's this is some debug board, and I guess the Flipper Zero debug board is based on it, and it's got some pins, and you can take the, pins and plug them into the Flipper Zero device itself. There's this 3D model thing, which looks like it's for the for printing the body. What I don't know is like where the circuit board is. Here's the PCB outlines. Is that it? Whatever dog is. Outline that dog. Here's a PDF. Okay, so this is just the like the physical contours of the board. So let's see if we can find the Flipper Zero PCB. Schematics. Here's a picture of it. Here's a drawing of the assembly. I don't know. Now I feel like I must find it. So what would it be written? Verilog. How about, is Flipper Zero open source hardware? Let's try Google. Is the hardware open source? The hardware is mostly open, but you absolutely can't recreate it. Whatever this is, go away, sign in thing. You need factory assembled components, like our PCB antennas for NFC and RFID, and some components like the displays are specifically made for us and can't be bought anywhere. Not to mention that Arduinos have a completely different MCU, Atmega in the Arduino and STM32WB55 in the flipper. And ours can only be bought as expensive Nucleo board or only in large quantities. So all of this stuff, like some of the hardware is I guess custom, or at least they have you need to buy it at scale to get it for a similar price. So there's no real hope in getting a look at like some hardware description of the PCB. It looks like, but we will look at the firmware, which is the software. I'm interested in an open source CPU. If you know one, an open source CPU. There was Open Solaris. I think that's wildly out of date, and I'm also not sure if it's still open now that Oracle owns Sun, right? A discontinued open source computer operating system. Oh no, not Open Solaris. The what was it? Open Spark, something like that. Open Spark is the complete design of Sun Microsystems UltraSpark T1 microprocessor. It was released in open source form. Chat now. Thanks, Oracle, but fuck off. It was named OpenSpark T1. Okay, so here's an open source CPU. What can you do with it? I don't know. There must be also open source hobby or model CPUs that were, probably never productionized. And then ARM, some of ARM must be open source, right? There's this open RISC thing, which is presumably some sort of RISC processor. And ARM open source. I don't know what it would be, like Verilog. What's the other one? Let's try Verilog versus VHDL. So here's some ARM implementation of a thingamajiggy. I don't know what a Verilog file looks like. At some point, I think we should read something like this. I'll send it out in the chat in case you folks are interested. Is the OpenSpark? Are you asking about OpenSpark or something else? But I don't know. I mean, so the OpenSpark was released as a real chip. Could it run modern stuff? Probably not too modern, but you could run a version of Linux on it, and it would probably do acceptably for things like having a web server or something, is my guess. But it would be prohibitively expensive to manufacture one, I assume. Okay. All right, so back to Flipper Zero. Here's the stuff. Let's assume that stuff is mainly in lib. Furry is that, I'm sure for furries, applications is probably stuff that's like on. I want to try to stay close to the hardware. Applications, I'm going to guess, is on top of whatever the layer in probably lib is. There might be some other layer in targets. I don't know about targets. Do they have any sort of guide to the source code? We have a firmware roadmap. What is this? Is this the roadmap? What on earth? All right, whatever that is. Okay, so let's look at what we have here, and see what we see. I don't know what a convenient layout for this thing is. Okay. All right. In targets, we have Flipper firmware. What does it do? RTOS. So that would be real-time operating system. Furry HAL. Hardware abstraction layer, I would guess. Furry core. Services and applications. So services, I'm going to guess, is kind of like daemons. They're just things that run in the background and provide services. So here's some Furry HAL include. Let's maybe pop this out. Furry HAL include. And then whatever F7 and F18 are. We have some Conscript. Conscript. I'm not really sure what that is. Here's some HAL stuff. So let's look at what furry is. A shoot 'em up video game. How about OS? How about furry HAL? I don't know if it's just a Flipper Zero thing. It seems to be maybe just Flipper Zero. Okay. Well, whatever this is, let's maybe move that to the back. Let's look at what sitecons is. Site init. Is this the website? BF to stir. Convert an element of get build failures to a string in a useful way. Display build status. So this is some sort of build stuff. What is scons? A software construction tool. It's some build tool. All right. So we don't need that. Applications. So we have examples, main, services, settings, system. Let's look at examples and let's look at main. And should we look at drivers? Sub-gigahertz. So here's the sub-gigahertz driver, it looks like. And maybe just pop that out into its own thing and come back to that later. Here are some examples. How about example thermo? What is .fam? Placeholder. Whatever. Some sort of config format it looks like. Wire thermometer. This example application demonstrates the use of a OneWire library with a DS18B20 thermometer. It also covers basic Gooey and input handling. So let's see if we can find out what this thing is. A thermometer, I guess. This, I guess, is the probe, and then it attaches to some chip. And I guess maybe also has a board. Something along those lines. Do you own the hardware? I do not own the hardware. Have any of you guys played with one? Either owning it or having stolen it or borrowed it? All right, so here's just the example. We're just going to peek at it quickly just to get a feel. All right, we've got some struct that has that's a union of a bunch of stuff, like the least significant byte of the temperature, most significant byte. User register 1, which is temp high alarm. I guess you can configure what to do if the temp is high, and similarly, what if it's low. I don't know how high and low are defined. I don't see anything immediately that would tell me that like you can set this is the high temperature, that's the low temperature. And then we've also got this struct which has a GUI, the viewport, a furry thread, a furry message queue, and whatever a OneWire host is, and float. Let's look at OneWire. Walmart. Arduino. Access OneWire temperature sensors. Okay, so some seems to be something about about thermometers. So we have example thermo, request temperature, commands the thermometer to begin measuring the temperature. All right, so we're going to call this furry critical enter thing, which is presumably going to do something like mutual exclusion. It must happen in a critical section, i.e. not interrupted by other threads. Yeah, so this is going to essentially disable other threads from accessing the hardware and maybe also prevent other kinds of interrupts. We're just setting success equals false, and we'll, I guess, set it to true if success becomes true. And then each communication with a OneWire device starts by a reset. So we reset it. After the reset, the ROM operation must follow. There's only one device connected. The skip ROM command is the most appropriate. It can be used to address all of the connected devices in some cases. I'm not sure why, but okay. So we, I guess, write some stuff into the ROM, into the read-only memory. And after the ROM operation, a device-specific command is issued. In this case, it's a request to start measuring the temperature. and then we call this ds18b20 command convert on OneWire. Why is convert telling it to measure the temperature? I'm not sure, but this looks like OneWire is maybe a general API for doing thermometer stuff, and then you're essentially passing in these specific codes that are probably just like bytes that are defined to be specific things that are understandable by the device. Okay, and then you do a bunch of stuff, but where is Gooey enter in? This function is called from the Gooey thread. So we have some input callback. All it does is put the event into the application's queue so it can be processed later. Okay, so we've got some message. We're going to put some message on the queue. All right. Gooey add viewport. So we're going to, the Gooey is going to add some viewport that's going to add some stuff. Whatever layer full screen is, maybe it's going to take up the whole screen. And what are we going to, this is just allocating memory and initializing the variables, it looks like. And then this is going to remove the viewport. So that's like the free opposite of the alloc. And then here's like the main. We're going to call thermo run and then thermo free. And then let's look up what example thermo run is doing. Starts the reader thread. Okay, so we're going to call HAL power enable OTG. So enable power to the external pins, configure the hardware in host mode. Start the reader thread. I guess that's the thread that's going to, well, as it says, talk to the thermometer in the background. And then we have an infinite loop. We'll wait for an input event. Input comes from the Gooey thread via the callback. Input event comes to the Gooey thread. Okay, so we're going to listen for the Gooey to send us messages, it sounds like. And then we're going to get the thing from the Gooey, I guess, and that's going to be some status. This application is only interested in the short button presses. Okay, so the thing we're getting from the Gooey seems to be essentially input events, like when you press the buttons. So if the status is not furry okay, and the event type is not input short, then we just ignore it. Otherwise, we get the key, and if it's the back key, we say that we're not running. So to stop reading temperature, you hit the back button, and then we signal to the reader thread to cease operation and exit if we're leaving the infinite loop, and then we do some joining and stuff. What I don't understand is, what have we written to the Gooey? Maybe in furry thread start. Start the reader thread. That's the thing. I don't know. Well, there's something that somehow sets the Gooey, but I'm not going to keep digging for it. And then here's main. And main has some interesting looking stuff like NFC. And IButton, bad USB. I think I've heard of bad USB. Bad USB. Bad USB is a computer security attack using USB devices that are programmed with malicious software. For example, USB flash devices can contain a programmable Intel 8051 microcontroller, which can be reprogrammed, turning a USB flash drive into a malicious device. The attack works by programming the fake USB flash drive to emulate a keyboard, which once plugged into a computer is automatically recognized and allowed to interact with the computer, and then can initiate a series of keystrokes which open a command window and issue commands to download malware. Well, presumably you have your thing password protected, but maybe, I guess if you're entering the USB, you may already be logged in. Okay, so this is interesting. This has some of the attack stuff. We'll close NFC for now. We'll open it later. And then bad USB, and then whatever, and then furry. Furry seems to be pretty central. And we have furry core. Dangerous to find. So this seems like event stuff, whatever kernel is, I guess maybe the kernel of the device operating system. Some memory stuff, the implementation of the, I guess, mutex, some sort of pub sub implementation, maybe related to the events. record or record. Here's a semaphore. Here's a stream buffer. This is kind of like classic operating system stuff. We have timers. This must be the real-time operating system, in fact. I guess that's what this is. Is that what furry is? I'm not sure. Then we have lib. We saw something about RTOS. Where was that? I'm not sure. So let's start with, I don't know why, but I want to start with lib. And let's also look up Flipper Zero operating system. That's ChatGPT. In the context of Flipper Zero, what is furry? What are you talking about, ChatGPT? You don't know. You don't know me. The Flipper Universal Registry implementation, says Gemini. It runs under the hood of Flipper Zero and essentially is responsible for managing how applications on the device function. Here's a breakdown of its role. Application flow control. It helps dictate the order in which different applications on your Flipper Zero run. Dynamic linking. Interaction management. Communication between different apps. While the technical details might involve managing threads and resources, the core idea is that Furry acts as a conductor for the applications on your Flipper Zero. So is this different from a RTOS? Furry is built on top of an RTOS. The RTOS provides the core functionality. Furry adds functionality. Okay, so what operating system does Flipper Zero use? It relies on a lightweight operating system called FreeRTOS, which I think we've looked at before, right? I think that's the RTOS we looked at. Yeah, cool. Gemini is saving the day. Thank you, Gemini. Okay, so this Gemini is claiming that it uses FreeRTOS. I'm not sure that's true. Yeah. Well, at least under targets, it's used. Scripts debug. It seems to be FreeRTOS-y. Okay. So on to the lib, whatever lib is. Oh, in fact, if we had just looked, by we I mean if I had just looked at the first thing in lib, it's the FreeRTOS kernel. Okay, and we have whatever bit lib is. Maybe something to do with bit manipulations. These seem like these are maybe third-party tools. And so maybe that's not so fascinating. Although we have Flipper application, FATFS should be the FAT file system. Flipper format, Flipper application, whatever IButton is, infrared. Yeah, these seem to be, so like this, I'm not sure what this notation means in GitHub, but this is maybe a Git submodule or something. And NFC. Let's just look at a few of these and just see if any of these seem to be created by the Flipper Zero people themselves. How about sub-gigahertz? Const. All right, we've got some math. I'm going to guess that sub-gigahertz is some other company. Do we get any sort of like, whatchamacallits? Copyright statements? Well, maybe it is. Maybe it is the Flipper Zero people. Maybe we could look at blame. And if blame is looking like actual development, then sub-gigahertz, support this, support that. And it's from these people. So this has some bug report associated with it. or rather issue ticket, and it seems to be in Flipper Zero stuff. So I think sub-gigahertz is a real Flipper Zero thing. Maybe also the same is true of NFC. Yeah, let's assume that's the same. So we have to figure out how to do this. Whatever BLE is, BLE profiles and extra services. What is BLE? HID service. Okay. So things are kind of like splayed out here. We have to have a plan. And I'm not sure what it is. Here's bitlib. So let's see what else is in lib. And then we have to think about what our plan is. So embed TLS should be the embed TLS is a small TLS implementation. So that's just like TLS or SSL support. I think sub-gigahertz is interesting. I think, what is signal reader? I don't know, but I guess we can open it. NFC is probably interesting just because those are things that people use Flipper Zero for. So here's just kind of like some of the hardware-y stuff is in this browser window. This is Furry, which seems like, if we believe Gemini, is kind of like a services layer on top of FreeRTOS. And I guess we can at least look at a few of these. And then we have some other windows here. One is applications/main. So these are going to be like applications built on top of the stuff. Like, let's see what's in sub-gigahertz history, et cetera, et cetera. I'm going to, I guess, close applications. And the drivers thing. I don't really know what targets is yet. But the abstract, so HAL is probably abstract, hardware abstraction layer. And I'm pretty sure. So HAL hardware abstraction. So I guess I'm going to ignore HAL and then possibly ignore Furry and stick to lib. So I don't know. We'll see. Here's bitlib. Brief increment and wrap around a value. We're going to give it an index and a length, and it's going to increment the index and take the modulus of the length, which I guess is what it means by wrap around. And then we have things like bit parity, even parity odds. These are libraries for handling bit level data, which you're going to have to do if you're doing hardware stuff. That's interesting, but not. I don't see it as part of the differentiation of Flipper Zero as a project. So we'll move along. BLE service HID stop report map. What is BLE? Well, HID service should be maybe like human interface daemon. Oops, I added an extra thing here. BLE app init. Let's try BLE Flipper Zero. Custom BLE spam messages. Maybe it's like a messaging protocol thing. Bluetooth, okay, so BLE is Bluetooth Low Energy, colloquially called BLE, formerly marketed as Bluetooth Smart. It's a wireless personal area network technology designed and marketed by the Bluetooth Special Interest Group aimed at novel applications in the healthcare, fitness, beacons, security, and home entertainment industries. Okay, reduced power and presumably also reduced range. Okay, so BLE applications. Let's try images just to see what's up. IoT, healthcare. So this is things like mobile payment, presumably it's stuff like Apple Pay. Health monitoring, maybe this is stuff like continuous glucose monitor would speak BLE to your phone or whatever. Indoor positioning systems, home automation. Okay, so that's Bluetooth Low Energy, and that's probably mildly interesting. Where did we start though? So this is just starting some service, and that's less interesting. Whatever I don't know what profile means, but this seems to be like service stuff as opposed to like reading from some chip. Here's Flipper application, and that's in lib. So let's look what an application is, I guess. We're going to include furry and some storage stuff. And we have stuff like preload status success, and some error, basically some error enum. And then some more error/success enum. One is preload and the other is load. And we're about preloading and loading, etc. Here's some stuff that has like a memory and address. A Flipper application memory map entry. So this is where some piece of memory is. And then we have application state, which has the count of mmap entries and the actual mmap entries, which are defined here, and some debug stuff. So that's really all it has is some the application state is just some chunks of memory, really. And we have this initialize. This thing initializes the application object. That's not so fascinating. Here's something to test whether something is a plugin. I don't know how we do that, but we're not in the C file, so it won't tell us. But we can load the name and icon. You give it a path, which is a furry string, and I guess some pointer to storage, and then a pointer essentially to the icon and the item name, and you can load that. Okay, so that's some application stuff. We're not going to look any more closely at that. Flipper format. Is this just like string formatting? Flipper file format. This is the file format. It's a fairly simple format for storing data in a file. We have some comments and some field name and then field value. And you can store strings and like int32s, uints, floats, and hexes. End of line is LF when writing, but CR is supported when reading. Okay, so this is this file format that's really kind of like key value style, it seems like. Although, yeah, okay, so key, key and then value with some types, with some restriction on the types. So we'll ignore that. IButton. You have whatever IButton is, it has workers and keys. So I'm guessing this is like you press the button on the device. IButton protocol. Not that. IButton key. Some allocation stuff. Resetting the IButton key. I don't know. Let's look at the Flipper 0 IButton. Is it a specific button? IButton. Flipper 0 supports a OneWire device communication protocol. Yeah, so we've seen OneWire already, like since the example, which is implemented in small electronic keys known as IButton keys. These are used for access control, temperament measurements, humidity measurements, storing cryptography keys, etc. Oh, okay. Let's see what one looks like. These things. Okay. I don't know if you click them. This thing says IButton click. But I feel like I've had these, and they're just like key fobs. And it looks like a battery. Is that big thing a battery? What is an IButton device? Let's see if we can see what's inside of it. What's inside? An IButton device uses a stainless steel can as an electronic communications interface. Each can has a data contact called the lid and a ground contact called the base. Each of these contacts is connected to the silicon chip inside, which I guess is the chip, this like little dot here, this little piece of whatever chip. The lid is the top of the can. The base forms the sides and bottom of the can. It includes a flange to simplify attaching the IButton device to just about anything. Two contacts are separated by a polypropylene grommet. By simply touching the IButton device to the two contacts described above, you can communicate with it through our OneWire protocol. Okay. But I see somebody using an IButton device. I want to know if it clicks or if it's something you like tap against a reader. That's Flipper 0. But I want non-Flipper 0, don't I? Or maybe I do want Flipper 0. Let's look what this guy has to say. I don't know. Let's try the Flipper 0 ones. So this seems to be like holding it up to some sort of reader. Okay. So stuff. That sort of stuff. All right. So that's IButton. So we have things like IButton key and was. But where's the cool stuff? So here we have some worker. I don't know what the IButton worker I.h is versus IButton worker.h with no I. Let's maybe open some of these C files. Maybe protocols. That's infrared. We'll get to that in a second. So worker has some which type of messages is sending and end, stop, read, write blank, write, copy, emulate, etc. That's, I think these are messages maybe to the worker as opposed to the IButton device. And so we get some sort of worker. We set the protocols to whatever protocols were passed in, and then we create a queue, and that's going to be like the worker message pool. And then we're going to set the worker to idle mode, and then create a thread for it to work on, and then we're going to return the worker. And we can also do things like set callbacks for the worker. Okay, so this is like worker stuff as opposed to IButton stuff. Here's protocols. Get group by ID. But where are the protocols? So you pass it in protocols and ID in some group info, and it seems to be doing some sort of search. If local ID is less than the protocol count, then we're going to copy some stuff from protocol groups to the info thing and do what? And then possibly return. This seems to be searching for stuff. Get protocols by name, but I'm not sure where the actual protocols are. Just kind of what I was looking for. Let's see if they're in the header. Yeah, I'm not sure. If we do a search for IButton, call. So here's some GUI looking stuff. We've got a scene manager and a view dispatcher. Here's the group data thing. More about group data. Here's an example. IButton protocol Dallas base. Let's look up this thing. DS1990. Can be read in less than 5 milliseconds. This is some particular IButton, a rugged data carrier that serves an electronic registration number for automatic identification. Okay, so this, I guess maybe by protocol it means like it's looking for specific like versions of IButton chips or whatever. Let's take a look at Signal Reader. And we've got some events like whether the half buffer filled. I guess presumably we filled half the buffer. We filled the whole buffer. Some event data, signal reader free, etc. So this is all of this code is really clean. Like there's a clean separation between this layer of code and anything that seems like it's closer to what is actually what's actually going on the hardware. But I think what I'm mostly interested in is looking at the stuff that's closer to the hardware. Some sort of parser. And I'm also not sure what like signal is supposed to be. We have ISO 15693. This is some ISO standard. Maybe the internet will tell us. For vicinity cards that can be read from a greater distance as compared with proximity cards. So are these like the traditional smart cards, or are those closer proximity? Okay. At any rate, this is some, I'm going to take it as like prox card reading. Okay. So first of all, we see this comment here about NFC refactoring. So maybe this is NFC related. We've got this parser stuff, but where is the actual parser defined? We have parser stop and parser start. And here's parser.c. And what are we importing? We're including bit buffer and including just the header. And we've got a state and a mode and a signal reader. And we've got like variables for things like have we detected the signal? What's the bit offset? What's the place to store the next byte? Place to store the parsed frame, etc. And then some enum. That's kind of like a state of the parser, I guess. And then parser alloc, parser free, parser reset, and some signal callback. You pass it an event, and it's void. Its return value is void, so it's presumably going to add some stuff to this context based on what the event is. And then parser start is going to start setting up the variables. And then we have the function, which is called parser parse 1 out of 4, which I kind of like. I kind of like that. But it's going to return a parser command, and it's going to accept the parser instance as input. And presumably it's going to start the parsing. It's going to do maybe about a fourth of the parsing. Oh, no. Okay. So we have this bit patterns 1 out of 4. So it's these 4 thingamajiggies. And we're going to iterate over the bytes to process, which comes in from this parser instance, and check next pattern. And we'll count we're going to call count of bit patterns 1 out of 4. I don't know what the count of thing is doing, but maybe we can find it at some point. And then we check if the bitstream buff at I is the outer loop index, is equal to the count of is just like how many there are, right? It's just length, I guess. So for each index, what we're really doing is we're checking whether that bit, really that UN8 is equal to one of these things, right? And then if it is, we're going to take whatever is in the next byte. I'm not sure what is in the next byte at that point. We're going to set it to the OR of itself with J, which is the second index. Oops. J, which is the second index, I guess the index of where we are in this bit pattern thing. And thing we're shifting by is the oh no, we're taking the next byte part times 2, I guess, and shifting it with respect to j. And then we increment the next byte part. Okay. So somehow, I'm not sure how to think about what exactly is going on here, but these are essentially values that are like encoding how we're supposed to interpret the stream of bytes that we're getting from this device. And this is, I guess, just setting like next bytes and whatever. But I don't know if we're parsing it into like a I don't know if we're parsing it into a set of like semantically meaningful bytes, or if we're just kind of like interpreting this stream of bytes as another stream of bytes. Then here's 1 out of 256, and presumably it's going to do something similar. Then we have parser run, and parser run is going to do what? Parser state parse SOF frame parse equals true. It seems like maybe we're reading frames, sort of communication or like networking frames. While command equals command processed, then we've got some parser state handlers. Where does command come from? So if we have bytes to process, we're going to set command to be command processed, I guess. And while this is command processed, we're going to set the new command to be the output of parser state handlers. And parser state handlers is just going to call parse 1 out of 4 versus 1 out of 256, which are the files, the stuff we saw above. And then if we succeed, then we'll return frame parsed. So I guess we got some sort of frame. And then what I'm going to do is I'm going to pop this 1 out of 4 thing into, I guess, Gemini, or maybe ChatGPT, and see if it can tell me how to interpret this. I don't know what XAI is, or the Mistral source code. I don't think I know what either of those is. Is Mistral the LLM? I think there are multiple things called Mistral. Mistral, a dry, cold, northerly wind. I intend to do, on my current list is Stable Diffusion. I don't think there's any LLM stuff in there. I don't know what XAI is. Elon Musk's new AI company. I'm not sure. But if you want to tell me more about the projects, like the source code you're talking about, I'll add them to my. I'm not going to promise that I will do them, but I'll add them to my list of possible projects to look at. Okay, so this parse 1 out of 4. Yeah, I know at this level. For each byte, it checks if it matches the bit patterns. If a match is found, it constructs a 4-bit byte by concatenating the index of the matched pattern. When a complete byte is formed, after counting all 4 necessary bit patterns, it appends this byte to parsed frame. Okay, so it's reading. It's looking for the specific bit patterns. It iterates through the. Okay. Okay, so explain it to me in more, in higher level terms. What sort of, what is the goal of this function? It's looking, I guess, to identify specific bit patterns in this data. These patterns are crucial for interpreting the data correctly. It's often encoded. Okay. Byte construction. So it sounds like ChatGPT is saying this is basically just looking for specific patterns in the protocol. Let's see what Gemini has to say. Tell me what this code does. Yeah, okay. So I will look at some LLM. I don't know if, I think for most LLMs, it's mainly going to be a bunch of weights, which I don't know if there's anything really to read there, but I will look at it and see if there's, if it's meaningful to look at the model itself. And if it doesn't seem so meaningful, then we'll look at something else, like possibly llama.c or whatever it's called, or maybe some of the code that's used to train these LLMs. And we may at some point look at some of the papers, because that's fun too. Okay, so it's parsing bitstream, blah blah blah. Loop condition declares another loop, blah 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 blah. Comparison compares with each element in bit patterns 1-4. If its match is found, it extracts the corresponding value, likely representing the bit pattern. It shifts the extracted value j left by next byte part times 2 and ORs it with next byte. This seems to be building a new byte by accumulating bit patterns from the stream. Then it increments the next byte part. I wonder if next byte is like looking for a specific, I'm not sure. It checks if the next byte part has reached 4, likely representing 4 bits of full byte in full. Okay, so what's with the, why is it doing the ORing with next byte? Was it next byte or next byte part? To position the extracted bit pattern within the next byte variable. Oh, okay. I guess next byte is the thing that's going to hold the next byte, and we're just, yeah. All right, that makes sense. Okay, and then we're just like that. Yeah, the next byte is the thing we're building up. I was thinking of it as the thing that was going to come next, and then we were building up the current byte. Okay, so let's move along. Let's take a look at sub gigahertz. All right. So in sub gigahertz setting.c, we want setting. How about blocks, devices, protocols, environment, receiver, registry, protocol registry, some worker stuff, transmitter. Maybe let's look at transmitter and receiver. Should we look at devices? I'm gonna guess devices is maybe just gonna be like chips you can order or whatever. Then decoder and encoder. And math. Okay, so here's transmitter.h. Some Alex stuff. Free, stop, deserialize. Deserialize and generate an upload to send. Okay, so you're going to give it a transmitter instance and a flipper file format thing. You've got some file that you've saved, and you're going to read the file, I guess, and send somehow the data in the file over this transmitter. And then we can yield, getting the level and duration of the upload to be loaded into DMA. Maybe it means yield as in the amount of stuff, like your grain yield. I don't know. Okay, here's receiver. Presumably it's going to be similar. You can allocate it, init it, reset it. We've got some callback. I guess set a callback upon completion of successful decoding of one of the protocols. And then we've got a filter. Set the filter of receivers that will work at the moment. I guess you can have multiple receivers, and you can select some subset of it. Search for a category by its name. whatever a cattery is. I thought a cattery was a place where they bred cats. Search decode base by name. Const car. A cattery is any building, collection of buildings, or property in which cats are housed, maintained, cared for, or bred. All right, well, I don't think that's what they mean by a cattery, but maybe it is. And let's maybe look at .c. So here's the block decoder. Subgigahertz protocol, blocks add bit. So you give it some decoder and a bit, which is a uint8. And we're going to just add the bit at the end of whatever is in decode data. And then we're going to say that we've, I guess, we've set that bit, so move along, and next time you call it, set the next bit by incrementing the count bit. You've got add to 128-bit. You can give it a decoder, a bit, and a head, 64-bit. And what are we going to do? We're going to check if the decoded bit count is bigger than 64 after incrementing it. Then we're going to take the head 64-bit and set it to, we're going to shift it over by 1 and OR it with whatever decode data is shifted by 63. So we're just shifting things over, I guess, to make room. Then we're going to set decode data to whatever the decode data is shifted over 1, and we're going to OR it with bit. So I guess we've added this to the head is the idea. And then we've got, so these kind of look like, it still feels like everything's like a little bit like a helper function. Here's receiver. I think we looked at receiver. And I think we looked at decoder, right? Did we look at encoder? You can set the bit array. Oh, okay. With some bit value, data array, etc. Set bit when encoding a hex array. What else do we have? Generating an upload from data. All right. And then here's some math. We have bit read. This is all just going to be like bitwise stuff, which I feel like you have to be in a specific headspace. Like whenever I've written stuff like this is like the only thing I do for like a week. And I only think in terms of this stuff, and then I kind of forget about how it works. So this is just going to set the value to bit. I don't know what value is supposed to mean. Type of value 1 equals 1. And we're going to take value and OR it with the 1 shifted over by bit. We also have things like flip the data bitwise, which is, I think we're just going to reverse it. I'm wondering if this is where it got the name flipper0, that it started as like all of this bit flipping stuff. We've got parity stuff. We've got CRC4, which is some polynomial encoding. I forgot that was the case. Moving along, let's take a look at NFC.c. We've got some enum that's got more like state, what state are we in, start, ready, etc. Communication failed, like whether the transmission succeeded. Then we've got an NFC struct, which has a state, a polar state. I guess we're going to poll, which makes sense. A com state, which I think we decided was communication state, and an NFC configuration state and a mode, and then FC. I'm not sure what FC is going to be, but FDT listen FC, max RX time FC, poll FC, some stuff about polling. RX should be receive time, I guess. Some event callback and a context, which is a void star. So it can be anything, and a transmission buffer and a receive buffer, and some worker thread. And presumably the worker thread is going to transmit stuff in the transmit buffer, receive stuff into the receive buffer, and I don't know yet what FC is, but maybe these are like configuration stuff. And whatever this is, why is this a bool? Okay, so this is a type definition. All right, furry HAL NFC tech. There's some NFC tech table that is, I guess, going to like map mode numbers to tech numbers. So, for example, this ISO 15693 is going to map to furry HAL NFC tech ISO 15693. We're basically just appending furry HAL NFC, or rather just furry HAL the front of it. Here's some error handling stuff, which we will ignore. And we have this NFC worker listener, which takes in a void start context, does some sort of asserting on the context, creates an NFC instance from the context, does some asserting, like the fact that we have a callback, and that the config state is that the configuration state is done. And then we set the state to NFC running, so we're ready to go, we're running. And then we call HAL NFC event start. Presumably that's going to notify any subscribers that we're starting NFC stuff. And then we've got some event data. We've got a place to store event data. And then doing some allocation stuff, blah, blah, blah. And setting the command to NFC command continue. And then we're going into this infinite loop. And we're going to, I guess, wait for the event, furry HAL NFC event, wait forever. Or rather, I guess we're going to set event to it. And then if event and abort request, then I guess we're going to abort and tell the callback that we're aborting. Or are we? Yeah, we're passing the event to the callback. And then there's a bunch of other events. So, okay, no, so we're not setting this event to that. This is, I guess, going to read events from wherever the HAL device is, the NFC device. And if we get the field on, then we'll set the field on callback. If we get field off, we'll set the field off callback, or rather tell the single callback that event has come in. If the event listener active, then we send the event type listener activated. So I don't know really what that would mean, but we also have the events like receiving is ended. And then I guess we get this event, then we call furry HAL NFC timer block transmission start, passing in the listen FC. I feel like I want FC to be like file descriptor, but it's a C, it's not a D. At any rate, it seems like if we find that receiving is ended, we're going to start transmitting. It seems like what it's saying. And then we are going to have this receive ending thing, and presumably tell the callback function. Do some copying of bits from the buffer. There's a bird attacking my window. You hear a loud bang every so often. It's like a robin who, I think he thinks the inside of the window is another rival robin. And I've tried to encourage him to not do that through a series of interventions such as scary looking fake owls, and reducing the reflectivity of the window, but he seems to be very persistent. Okay. And then we're going to do some reset and stuff. So this is finally looking like we're actually doing some work here. So we're copying bits from buffers. We've got some state that we're really keeping track of. I wonder if this NFC is used for all of the different protocols somehow. We've got some handler and handler stuff. Okay, let's move on. Here's infrared. I guess I'm not so concerned with the worker. I'm more concerned with the encoder decoder. And then encoder decoder seems to have maybe different implementations. So Pioneer, I think a Japanese company, Samsung, maybe Korean. So Samsung is Korean. Pioneer is what? Something about a Japanese multinational corporation. Yeah, I was right. I was really just making that up. Is it Mitsubishi? No. Okay. All right. So these must be different, like infrared devices, possibly like TVs, RCA. I think at one point it was American. I don't know. They still are. NEC. I think these are all companies that happen to manufacture TVs. I don't know if these are all for like TV remotes or for something else. Protocol description. RCA.php. So we have some preamble mark, preamble space, pulse distance width modulation. This is like pulse modulated. And then pulse up to period, preamble repeat mark. So this seems like we've got this protocol, this like infrared stuff, and we're kind of just modifying it for the different manufacturers. Blah, blah, blah. The RCA, so basically took a remote, an Xbox remote that uses the RCA protocol, and this stuff. Okay, maybe these are these are all named after TV manufacturers because like they were some of the first companies to have ubiquitous infrared devices, and so those were the ones that defined their own protocols, and maybe these are just the mutually incompatible protocols, and everyone just picks one or something. At any rate, we have some RCA specific stuff, but I imagine that a lot of it, the implementation is going to be like taking this table and like using it to set some stuff. Okay. Like address length is 4, command length is 8, frequency is common carrier frequency, common duty cycle, etc. Okay. And then we're setting this stuff, timings. Preamble mark is this RCA. Okay, so this is the stuff that comes from the table. And here's infrared.h. And we've got some enum of what the protocol are. These are the different protocols. And we've got this infrared message, it knows which protocol it's in. And it has an address and a command and I guess repeat, whether it's repeated or whether you should repeat it or something along those lines. And then we can initialize the decoder, and the infrared decode will have this decoder handler a level. What is level? High, true, or low, false level of input signal to analyze. It should alternate every call. Otherwise, it is an error case. So I guess that high is on and low is off? Or I don't know. Maybe high and low are both versions of on. At any rate, there's a duration. The duration of the steady high-low input signal. Infrared protocol, high-low. Let's look that up. Understanding the basics of infrared communications. The logic gates are encoded by using pulses of different lengths to distinguish between high and low. So I guess that's just how you're sending binary. Instead of on and off, you are just sending high versus low, and those are just like the amplitudes, right? Okay. Is that what? Hang on. Is that just the same as pulse modulation? Pulse modulation schemes aim at transferring a narrowband signal over an analog baseband signal as a 2-level signal by modulating a pulse wave. And a pulse wave is like this. So I think that maybe that's what's going on. So we have what I'm going to think of as high and low, and then the underlying carrying thing is like the infrared light wavelength, and then on top of that we're layering this high-low stuff somehow. Okay, and then we've just got a bunch of stuff like getting protocol name, and then presumably in the infrared.c, we would get like a framework that takes the implementation details from the different protocols, like the RCA protocol, and uses them to feed the parser. We've got this infrared decoder stuff. It has some stuff about allocation, decode, reset, check ready, free, and so on and so forth. Why do we have so many of them? It's a list. Okay, so the list is just the different protocol versions. Okay. And so I guess we're just going to index into the list based on which version we detect. And then I think I'm just going to move on. We're at about an hour. I'm having trouble talking too long without coughing right now. So I think I'm going to wrap it up and just make sure there's nothing that I really wanted to come back to. Well, this is furry stuff, but I think I'm okay skipping furry. I mean, this is all interesting. This is a nicely laid out project, but I'm going to leave it there. So let's say a little bit about what we saw. One is that, first of all, I think we really only kind of scratched the surface, especially if you are interested in the hardware level. A lot of the hardware specific stuff is going to depend on which specific device maybe that you're communicating with. So we saw that, for example, in the infrared, but also in some of the other protocols, like the OneButton stuff, that it might depend on which specific chip version the OneButton device has. And then on top of that, there's just the layer of well, we're working with any particular OneButton device as opposed to an infrared device or a low energy Bluetooth device. And then all of those libraries get the device itself, the Flipper Zero device is has a Gooey. And we didn't look at really any of that, and it has applications, but it's built on FreeRTOS as the real-time operating system. Then it has this furry layer, and the furry layer seems like it's handling mainly things like communication channels, event, like subscribing to events, file format, stuff like that. It provides a level of utilities that you would expect, for example, in something like the Linux operating system, whereas FreeRTOS is more like the kernel. So, and then for the Gooey, for example, they only really have to worry about one screen because they're not supporting any possible number of screens. It's an embedded device, and they know exactly which screen they're using and what it looks like and how big its width is. So you imagine that some of that will constrain how complex the code has to be. And that leads really that pushes the complexity toward just this is a device that has to interface with the world. And that interface, that complexity comes in the form of the fact that it has to support multiple different kinds of protocols. And those protocols, there might be little variations depending on which chip reader you're using, or et cetera, et cetera. Hello. So that's it. I'm actually holocoric. I'm actually just ending. But yeah, that's it. And so thanks for watching.